Good morning. We are moving on into Chapter 5. It's a continuation of what we were looking at in Chapter 4. So we're going to be going into more detail, setting up forces. So let's just move ahead and take a look and see what we've got going on here in Chapter 5. So the first thing we want to include in Chapter 5 is we want to introduce the idea of frictional forces. We talked about that a little bit in Chapter 4, that all the surfaces we were looking at, they were all frictionless, and that was really an idealization. Almost always there are going to be frictional forces present in the examples. Now, one of the things they point out here, which I think is important, is friction's complicated. There's no simple formula that tells us how friction works in all different cases. Now, what we do use are some simple formulas to kind of estimate how friction behaves. And so let me start out by, let's see, they talk about there are two different types of friction that we want to consider here. One is when we have an object that is sliding along a surface. And so for this, let me grab my textbook. So there's my textbook. So we could say, well, here's the textbook, and here's a table surface, and it could be that when I push on the textbook, the textbook doesn't move. And that would say that there's friction holding the textbook in place. If I push from the left or push from the right, and there's no motion, we know from experience that, well, that's friction. Now, if we push hard enough, we can make the book slide. But there continues to be friction, whether it's sitting there at rest or whether it's in motion. Now, the friction when it's not sliding, when it's sitting there and I'm pushing and it hasn't started to slide, we call that static friction. When it does slide, we call that kinetic. Now, the formula, this is an approximation, it's a rough model that we use for friction, and it works reasonably well in a lot of situations. In lab, we've got a frictional force lab that we'll be taking a look at, and there we'll be able to go in and identify how this works. Now, what we say is that this sliding frictional force depends on the normal force. Now, that's kind of interesting. What we say is that, if I have a textbook and I set it on a surface, there's going to be a normal force acting on the object. And if it's sliding along a surface, there will also be what we call kinetic frictions. Now, these couple slides here are really talking about the kinetic and static friction, so I'm going to move ahead. What we typically find out is that the static frictional forces tend to be larger than kinetic. And so maybe if you're helping somebody push a box across a floor, for example, or maybe you're pushing a box across the floor, and you're thinking, if I can just get this to start sliding, it's going to be easier. And so if you take a look at what we call the coefficients of static friction and coefficients of kinetic friction, here are the two symbols that get used. What we find is that this coefficient of static friction tends to be larger than the sliding. It's more difficult to get something to start sliding compared with making it continue to slide. Now, if you look at the materials here, notice that it's always two different surfaces that we're talking about. So kinetic friction is going to depend on both surfaces. If it's textbook on this table, then it's this particular cover of this textbook against this particular surface of this table that are going to determine what the coefficients of kinetic and static friction will be. Okay, so you can kind of look across that table and notice, tires are made out of rubber, for example, or some kind of engineered rubber-like material that can produce a lot of static friction. So some surfaces more friction, other surfaces not so much. So let's get started. Maybe with an example we can be more clear about this. Here's a force diagram. So here's the gravitational force acting on, well, the mystery box is back, I have to say. In fact, in chapter 5, in this section on friction, what we're going to do is we're going to go back and we're going to redo every example we did with the box. And this time we're going to include friction. So we'll go back and kind of redo everything. That's a good systematic way to introduce friction. So this time, I've got a gravitational force. Here is a normal force due to contact with the table surface. And what we're doing is we're pulling on this or pushing on it, something where we're, trying to push this object along a surface. But there's a frictional force in place. So as we were talking about, what happens if I start to increase that force? Well, with this particular object, what they're saying is, what happens if we push with no force at all? What if FA is 0? What if I start pushing with 10 newtons? What if I push with 20? About 38 newtons. And what about 40? So they've picked some different forces that you can push with, different amounts, and then they're going to ask what's going to happen in terms of friction. Now, what they're telling us here is that the static frictional force is 0.40, no units here, and we'll see how these formulas work. The coefficient of kinetic friction, 0.30, and so what we're trying to do is determine what will happen in all these circumstances. Let me jump ahead a bit to my own diagram. So here is the diagram of the setup. And so what I did was this. I thought, well, let's just systematically go through and look at what happens if we push horizontally with these different forces. Now, just to get some background here, it's a 10 kilogram object. The gravitational force acting on this then in Earth's gravitational field is 98 newtons. And that tells us that the normal force is 98 newtons. So the formulas that we kind of went through quickly, I feel like these are going to be more understandable once we start looking at them in an example. So the two calculations we can do for friction is, first of all, I'm going to look at the kinetic friction. Let me move to static. Let's start with static. So those earlier forces were saying that static friction could become as large as mu sub s times n. Now, n in this case is 98 newtons, and that says that the static frictional force could become as large as 39.2 newtons. Now, what that tells us then is, well, if I push with just 0 newtons, it's not going to start sliding. What about 10? Nope. What about 38? And it looks like this is not enough. It's just going to continue to stay at rest. So what we can do for each of these examples is ask, well, what's the static friction at that particular point? And the static friction, notice that if I'm not pushing with anything, there is no static frictional force opposing that. If I start pushing with 10, static friction pushes with 10. With 38, static friction pushes with 38. But notice, for this particular set of surfaces, the static friction force will go as high as 39.2 newtons, but it won't go higher. So that says that if I push with 40, I have overcome the maximum static frictional force, and now the object is sliding, and it's no longer static friction that we're dealing with. It's now kinetic friction. So that's the crossover point. The crossover occurs when we hit the maximum static friction. So now that it's sliding, we got to go back and calculate kinetic friction, and for that we'll use the other coefficient. Now, I didn't write those down anywhere. I should have. Let me go back and just remember the coefficient for static friction, mu sub s, is 0.40. Mu sub k is 0.30. And so what we've seen here is we've been applying a larger and larger force. And as we apply a larger and larger force, at what point will this begin to slide? And it's once we hit that maximum number. The maximum value we calculated was 39.2. And so once we cross that threshold, then it begins to slide. And now the friction force is less. So now it's gone into kinetic friction. Now they've even made this a little rough. It kind of goes back and forth. And that's saying that on most surfaces, the friction isn't even a constant value in reality. We estimate it. But the kinetic friction is not necessarily perfectly uniform along those surfaces. The surfaces themselves might not be perfectly uniform. There could be different conditions along those surfaces. All right, and so again, I guess I should add that in, maybe write that in here. Mu of S equals 0.40, mu of K equals 0.30, because those are the numbers we're going to use to calculate the friction. Now, a couple things we want to ask here is, okay, these are the formulas, yes, I can plug numbers in, but why do the formulas have that look to them? Why is it that the frictional force is proportional to the normal force? Well, if I had a 10 kilogram object here, that means that the two surfaces are going to be pushed together with a force of 98 newtons. There's a force pair between the two surfaces, normal force, that's 98 newtons. Now that's pushed together with some amount of force, and so that makes it more difficult for those two surfaces to slide past each other, and that's why the friction is going up. So if this were, let's say, a 20 kilogram object, what if we're 20 kilograms instead of 10 kilograms? Well, that would double the gravitational force, and that would mean that the contact between the two surfaces would also double. And if that doubles, then it says what we find is that the maximum static friction force is also doubled. With the two surfaces being pushed together with twice as much force, or 5 or 10 times as much force, that means the frictional forces will go up by that same factor. And that's our simple formula. And again, in lab we'll find out that it's not bad. It's a pretty good approximation, and it allows us to incorporate friction into our calculations. Okay, but always be aware that with friction, those coefficient numbers are, there's a little variability, or sometimes a lot of variability to those coefficient numbers that we have. So that's where we're headed here. Now, so in this problem, A, B, and C, object did not move. It remained at rest, at rest, at rest. But once we hit 40, that exceeded the static friction, so we crossed over to kinetic friction. And then what we can do is say, this object, I need an acceleration arrow too. So here's an acceleration arrow right there. All right, or up here maybe. So the acceleration will depend on force that we're pushing with minus the frictional force divided by m. Remember, with the frictionless surfaces, it was just F over m. Now we're into chapter 5. Friction is a part of our setup, and this is going to be 10.6 newtons. That's the difference between these two forces. I'm pushing with 40, the friction is 29.4, gives me 10.6, and then I have to divide through by the inertia. And so dividing through by 10 gives me 1.06 meters per second squared. All right, here's another good example. I think this is probably something that you guys are familiar with. Here's an object. It's a box. I don't know if it's the same 10 kilogram box. But what they're saying here is you could take an object like this and you could push it against a wall like this. Now, you notice it started to slide, so I had to push harder. What they're saying here is, how hard do I need to push to make sure that this thing doesn't slide? Now, the force diagram for this looks like, well, there's gravity downwards. We need some kind of an upwards force, and the only upwards force available right now would be that frictional force with the wall. Now, there's also a frictional force due to my hand, or it could be that my hand is assisting that also. There's some friction there. But what we've got are contact forces, a normal force here, actually a normal force here also. And so we've got these two normal forces coming in like this. And then there's going to be some amount of friction, static friction, that allows an upward force. if that static friction is large enough, it can offset gravity and I can just hold something up against the wall. Now, I guess in this problem, they're assuming the person's hand is completely slippery. They don't say it, but that's kind of what's assumed in the diagram here. They're assuming all the upward frictional force is coming from the wall. Now, let's see what the numbers would look like on this. And you know from experience, if you hold the object with not a lot of force against the wall, it'll slide down. So here is that same thing. Here's the normal force. Now I drew little zigzags here to remind myself that the normal force extends all the way along where the contact is being made. So what we want is this. We want enough upward static friction to be equal to mg, and such that there's no acceleration in the y direction. Now, the maximum static force that we could hope for would be mu sub s times n. So again, what we're assuming here, I guess, is that the hand is slippery. You know, maybe there's, I don't know, something slippery you've put on your hands. And so you're really just counting on the friction force along the wall. N is going to be equal to F, so there's no acceleration in the x direction either. So we're going to be pushing with a force here, and that will set up a normal force of N. Now, we know that the static friction force could be anywhere between 0 and some maximum value. Now the maximum value needs to be equal to, the maximum value will be given by mu sub s times n. So what we're saying is that the frictional force, the maximum frictional force, has to be at least as large as mg. And if we set that equal to, since n is the same thing as f, we can write that as mu sub s. And that tells us from the formula we have right here, if we solve for f, we need to push with a force at least as large as mg divided by mu sub s. So if the mu sub s gets too small, if the mu sub s is very small, we're going to have to push with a much larger force. So I just made up some numbers here, I think. I said, for example, if mg worked out to be 20 newtons, then, and mu sub s is 0.4, that's what it was earlier, I would have to push this object against the wall with a force of at least 50 newtons. Okay, which is it's a pretty good, that's a 10-pound force pushing this against the wall. So this is a good one to look at too. It's, you know, I always like these examples where the normal forces are on an incline, or else they're on a wall, they're vertically oriented, the forces themselves are horizontally. Just, you know, as a reminder that normal forces can be in any direction, and frictional forces can be in any direction. Does not have to be a horizontal surface. All right, here we go. We're going to look at another example that we saw in chapter 4. That was pulling along this 10 kilogram box. 10 kilograms, force of 40 newtons, 30-degree angle. I think you'll see that example was there. The only thing that's been included is friction. Now, they're saying calculate the acceleration. So if this object is accelerating, that means its velocity is changing. That means that there's got to be some sliding taking place here. So apparently this object is going to slide. Now we can go in and take a look and see if that's the situation. So here is the box. Here is mg. Here is the normal force. Here is the force we are pulling with. And then in the problem, they talk about how much acceleration is there. So here's the frictional force. Let's see, it's 10 kilograms, mg is 98 once again. The force we're pulling with, 40, yeah, all the same stuff. Now, they've given us a kinetic coefficient of friction. I guess we should go back and take a look at static. We've got that on an earlier slide, so we can go back and take a look. Let's take a look at the acceleration formula for this force diagram. So it's taking a look at all the forces, dividing through by m. And the force in the forward direction would be F cosine of theta. So F cosine of theta is in the forward x. Friction is opposing the acceleration. It's opposite. We'll put a minus sign in for that, and then divide through by m. Now, how are we going to calculate these forces? We know the force and the angle here. How are we going to calculate the kinetic friction? Well, the kinetic friction, let's use that in terms of the coefficient of friction times the normal force. Now, in this case, if you remember, the normal force is not just mg. If we take a look in the vertical direction, we'll call that y, it would have to be that n plus f sine theta. So we've got this force, F, divided into F cosine and F sine. So N plus F sine theta equals mg. When we solve for N, that's mg minus F sine theta. And that's telling us that the normal force, the amount of force that this surface, the amount of force perpendicular along that surface is 78 newtons. So that's 78 newtons. That can be put into the normal force here, and then 0.3 times 78 gives us 23.4 newtons. So 23.4 newtons is the amount of kinetic friction force that we'll have. Now, I guess I was a little concerned here, but I didn't really go back in and calculate this. I guess we're assuming it's sliding in either case. So it would be useful to go back and ask, is there enough force here to offset the static friction force? Because if it's starting at rest, maybe it doesn't move. That's one possibility here, depending on the coefficients. So what would that become here? This would be the normal force. If we put in the static effect, the 0.4, instead of the 0.3, that force is going to become, I don't think it's going to get as large as 40 times. We'd have to go back and check and see. Anyway, take a look at that. The acceleration in the x direction then would be given by F cosine theta minus the kinetic force divided by mass, and that's giving us a net force in the x direction of 11.2 newtons divided by those 10 kilograms. That would give us an acceleration in the forward direction, 1.12 meters per second squared. All right, here's another setup. I think we looked at this one also back in chapter 4. Here's a couple of objects. One is at 2 kilograms, one's at 5. We've got a connector string between them. We've got a pulley. The pulley has really low mass because it's not chapter 10 yet. So for now, the pulley we're not going to consider as having mass. The string, we're going to say the mass there also is insignificant. Now there's a kinetic friction between box A and the table, and that's at 0.20. So the kinetic friction's a little lower this time. They're not telling us about static friction, so we're assuming that, that this will be sliding. So the kinetic friction tells us that the object here will be moving, and then this object will be dropping. So here's the force diagram for object 2, or object B. Tension is upwards, mg is downwards. Now this is m2 or mb. For the sliding object, we have a normal force, have a gravitational force, there's a tension in the string, pulling, or the cord, pulling this forward, and there's a friction force holding it back. So those are what the force diagrams look like. Now it's saying that there is an acceleration that takes place, and so that's saying the tension is going to be larger than the static friction. Let's see what happens. So here is the setup. Here's my drawing, and of course I took the A and B and turned them into 1 and 2. Those are the masses that were given. And then this was the kinetic coefficient of friction. Here is the force diagram for object 1. N will be equal to m1g. The acceleration will be given by tension minus kinetic friction divided by m1. If I solve now for how much kinetic friction do I have, remember the kinetic friction, we're going to model this as mu sub k times n. And n is equal to m1g. So I'm able to get an expression for the friction. And this is how the coefficients of friction work. So I can write this as a coefficient times m1 times g. When I substitute that in for the kinetic friction, I'm getting an acceleration t minus mu sub k m1 g divided by m1. Now, I've solved that for tension because I've got another object, object 2, and I'm going to need to solve for both objects. This is the same thing we did back in chapter 4. I need to solve the acceleration for both objects and then recognize that the acceleration for each object, they match. So there's not two accelerations taking place here. There's just the one acceleration that we're solving for. This acceleration is the same as that one. Also with the tensions are the same tension. So I can take the acceleration equations, solve for tension for this one. Same thing with object 2. Here the acceleration is downwards. The acceleration will be in terms of the forces divided through by the mass. The force driving this is gravity. Tension is holding back, divided by m2. When I solve for the tension here, I find that the tension is equal to m2g minus m2a. So the higher the acceleration here is, the lower the tension would end up being. In any case, algebraically, I can take those two formulas and set them equal to each other. Now, this is another one of those examples where I'm going to highly recommend that you practice solving these algebraically. Don't put numbers in. Often students are thinking, well, if I put numbers in here, I can just start doing numbers, but you really can't until you get to those lower steps in any case. And by leaving this as algebra, what we can do is go through, here are the two expressions for object 1 and object 2 set equal to each other, and then we've solved for the acceleration at the bottom. Okay, final step in the algebra, the acceleration of the system of objects, m2g minus mu1 m1g over the combined masses. Now we've seen this before, where when we solve for the acceleration of the system, in the numerator, what we're getting is the net external forces. In the denominator, we're getting the net inertia. Now, back in chapter 4, this whole thing was being driven by gravity. But now, in addition to gravity, there is a frictional force, and the frictional force is opposing gravity. And so the acceleration won't be as large as it was back in chapter 4 when we had frictionless surfaces. Okay, so putting the numbers in now, and so this algebraically, it's really nice to be able to see that and see how this will work. So for example, you could imagine a situation where the acceleration is 0, and that would be saying that the frictional coefficient is large enough, and the masses, the values of the masses are such that it doesn't slide. All right, and so if the numerator, for example, were to be 0, that would say no acceleration. That would mean you could slide at a steady speed. But if the if the numerator became negative, the negative would say that the object is actually slowing down. I give it a push, but because the frictional force is so large, it slows down. So let's see which case it is. When we put the numbers in, the mg pulling object 2 is larger than the frictional force we have on object 1. What was the coefficient on this one? Just trying to think of how the numbers worked out. It was 0.2. Object 2 was only 2 kilograms. So in this case, this was 2 kilograms, this was 5, I guess, were the numbers for this, and the coefficient was a 0.2. So you can imagine if the frictional coefficient were larger, by a factor of 2, then these two would cancel out and you'd have no acceleration. For the numbers that they've given us, we do have an acceleration, and it's 1.40 meters per second squared. All right, so another good example, so if you guys have questions on these, definitely stop by office hours and let's get these looked at. It is kind of handy that we've got another resource in solving the problems is to go back to chapter 4 and review how they were solved when there was no friction. So you can put the chapter 4 example and the chapter 5 example side by side and see where those frictional forces, what effect they have, what changes will they introduce. Now another example that we looked at in chapter 4 were objects on inclines. So here's a skier, I guess it was a skier before, right? On an incline, and that was the force diagram that we had come up with for this object. Now in this case, we do have a frictional force, so since the skier is sliding downhill, the frictional force will be opposite the direction of the sliding. So the velocity is in this direction, the frictional force is back in the opposite direction to that. Now, as we've pointed out with all of these incline problems, the easiest place to make an error in the diagram is with dividing the force, the gravitational force. So pay attention, as always, on inclines to the gravitational force. There's going to be a cosine theta component and a sine theta component with, if the angle is the angle of incline, then what we'll find is that the mg sine theta is along the incline and mg cosine is perpendicular to the surface. So the diagram looks like this. If you remember, we started with an xy coordinate system, an xy coordinate system, and then we rotated it by an angle theta. So everything rotates, the x and the y axes both rotate by an angle theta. And that takes our gravitational force, and that rotates the box that we're using for that gravitational force component. And so mg cosine theta, mg sine. Make sure that you're understanding that force diagram. Now from that, we're going to say that the acceleration then is along the incline. And this is going to be an mg sine theta minus, this is our kinetic friction. So mg sine theta minus kinetic friction divided by m. And the kinetic friction can be written in terms of a coefficient of friction. So this will be mu sub k times n, and the n for this diagram, n is equal to mg cosine theta. So that n substitutes in, and now we have a frictional coefficient, a frictional force of kinetic friction, mu sub k mg cosine theta. So now we know how much to subtract off away from the mg sine theta. So I've got two forces going on. I got the mg sine theta here, I got the frictional force opposing that, and so the acceleration will be mg sine theta minus mu sub k mg cosine theta divided by m. Now, notice what happens algebraically here. This is kind of interesting. Notice that the m's on top cancel the m's below. The m's cancel out. And the reason why is because, well, gravity is proportional to mass. So the gravitational force is proportional. But the frictional force is also proportional to mass, because for many of these examples, the mass will determine the normal force. The heavier the object, the larger n is. So since this is proportional to mass, this is proportional to mass, this is proportional to mass, everything's proportional to mass. When we solve for the accelerations, the masses drop out. So it says, if I'm sliding different boxes with different masses along this very same incline, how will the accelerations compare? And since the coefficient of friction, if the coefficient of friction is the same for those, then if I've got the same mu value and the same incline, then all the accelerations will be given by that. So it depends on angle, and it depends on the coefficient of friction, depends on the properties of the surfaces. But it's really independent of how heavy, how much mass the object has. Now, what they've told us in the problem is, so that's the formula that we derived, and again, that's one of those formulas that you can kind of stare at and think about, what is that formula telling me? And it's saying, for a given set of angles, or a given set of friction coefficients, you may or may not have an acceleration. Maybe you do accelerate down the incline, maybe not. If the incline tends to be larger, it's more likely you will have an acceleration. If the angle is smaller, maybe not. If the coefficients of friction are larger, that's going to oppose the acceleration. So again, if there's a lot of friction, maybe the angle's not that big, it won't slide, and it won't have an acceleration. Now, in this case, they said, what happens if it slides down at a constant speed? So if we've got some kind of a balance going on between friction and the angle, such that it slides down at a steady speed, well, we can use our formula and set the acceleration equal to 0. So setting the acceleration equal to 0 means that I'm going to take this sine theta, which derived from the gravitational effect, minus mu sub k cosine, which follows up on the friction, and set those two equal. So if I set these two equal, the acceleration will be 0. That tells me mu sub k needs to be sine theta divided by cosine, or tangent of theta. And since we know the angle, that is the, we can calculate the coefficient of kinetic friction that would be needed to prevent the skier from picking up any speed. Okay, so the skier wants to be able to go down the hill and not be slowing down, not be speeding up, but maintaining kind of a roughly constant speed all the way down the slope. Now, that's a pretty high coefficient of friction. So the snow here is, for some reason, has a lot of friction to it. That's a really large value. That surprises me. So, yeah, that's unusual. Those numbers came up. All right, here's another incline problem. So, and let's see what we have going on here. Here's an incline. It's at 37 degrees, and one of the objects, object 1, is 10 kilograms. Object B, we haven't decided how much mass it has yet. Box A, box 1, is 10 kilograms, 37 degree angle, lightweight cord, massless, frictionless pulley, connected to second box 2. If the coefficient, now the coefficient here is back at, this is for static friction, it's back at 0.40. Determine what range of values will keep the system at rest. So what we're trying to do here is this. You can imagine this. We've got this object, it's sitting on a surface, there's a good amount of static friction. Now, if MB, if M2 is not very large, then what's going to happen is this is not going to produce much tension, and that we're going to need a larger frictional force to hold this in place. So that is, let's see which case is which case. Yeah, so if mass B is small, then we're going to need friction to be operating in this direction to prevent the box from sliding down the incline. Now the other possibility is, well, what happens if MB, we keep making MB a little heavier and a little heavier and a little heavier? What's going to happen? Well, at some point, it's going to be large enough to balance this without any friction at all. And then if MB gets really large, it's going to tend to pull MA back up the incline. If you go back and look at the example from chapter 4, you'll see that there were ranges of MB, that allowed this to slide down the incline. Larger values of MB would pull the object up the incline. And now friction is going to reverse. The static friction could go either direction depending on how large mass B is. So what we're guessing here is there's a range of values. There's a range of values for MB within which the system will stay at rest. There will be enough static friction. Let's see how much. There's a lot of stuff to look at in this, so let's take a look. Here is the setup. Again, I've switched over to M1 and M2. Here are the forces acting on object 2. So I've got tension, I have M2G. Now for object 1, what we've got is we've got M1G sine theta and M2G sine theta. We've got a normal force, we've got tension, and I guess I drew this for the case where M2 is large. So the frictional force, it could be, I want to solve for a maximum value, but it could be in either direction. So let's see how that works. For the drawing we have here, if there is to be no acceleration, so the object it starts out at rest, and if the acceleration is 0, then it stays at rest, is the idea. So, so the forces then would balance out. Now I've written this as t is equal to m1g sine theta, but then I put plus or minus. I don't know if this is a good idea. I'm trying to solve both cases at once. So I'm trying to solve for the possibility that static friction is in this direction, or it's back in the other direction. So this is telling me how much tension I would need to have in the string for each of those cases. So I've gone through and substituted in right here the expression for the maximum value. This was just saying static friction, but now I'm ready to move ahead and use the maximum value for that. And so tension, it turns out, tension can be substituted with M2G. So tension is equal to M2G here would say that there's no acceleration. So I've substituted that expression in and then set it equal to the whole tension expression. Now what happens in this case is that the G's are canceling out. What's happening is I've got forces that are proportional to the gravitational field. And so the G's, the gravitational field factor, is canceling on these two different sides. And that means I can come in and solve for M2. So M2 is equal to M1 times the sine of the angle, that's 37 degrees, and then depending on which direction the friction is in, I'm going to write that as plus or minus 0.40 times cosine of 37. So now I can solve for those two possible cases. Now for the case where M2 is really low and the frictional force needs to be in this direction. Where the frictional force needs to be in this direction, and M2 is really low, and this frictional force is preventing it from sliding. In that case, M2 could be as low as 2.82 kilograms. Now, if the mass of M2 drops below 2.82, what happens? If that mass drops below 2.82, then friction alone is not enough to prevent object 1 from sliding down the incline. So there's not enough static friction to hold object 1 in place. So I'm going to need some assistance from M2. I'm going to need at least the 2.82 kilograms. Now, if M2 starts to get really big, we said the problem then is that M1 could be pulled up the incline. And to solve for that value, we can put the plus sign in here. And putting the plus sign in, M2 now can be as large as 9.21 kilograms. If M2 is larger than 9.21, then there won't be enough static friction to prevent object 1 from sliding up the incline. Okay. So this is a good example, I have to say. It's a little complicated, it's got some details to it, but that's what's nice, is you have to realize that the static frictional forces could be in either direction. And again, I'm hoping this is an example where you can kind of intuitively see, oh yeah, if M2 is too big, it's going to slide one way. If M2 is too small, it could slide the other way. And those are the limits of the mass. So any mass in between those two values for M2, and it'll stay at that, at where it is. Now, in part B of the problem, they change things around, and they're saying this. They're saying that, what if M1 and M2 are both 10 kilograms? Well, let's go back and see, because we kind of solved for that. If M2 is 10 kilograms, that's above and beyond the limit. So it's telling us that if M2 is at 10 kilograms, there won't be enough static friction to prevent the object from sliding up the... So that's what's going to happen. We're outside that range, and we're outside that range on the high side. And so we can now say, hey, the acceleration is going to be down for M2, it's going to be up the incline for object 1. The forces we have are m1g sine theta, opposing the acceleration, and we also have the friction, the kinetic friction now, mu sub k m1g cosine theta, also opposing this. So what's happening now is I've got gravity pulling in one direction, and that's going to be m2g minus m1g sine theta minus the frictional force. So I've done this as one object. We could go back and break it down into two separate objects and take a look and see what those acceleration forces would look like. But this is both objects together, dividing through by the inertia. And that tells us, well, I put numbers in. So the gravitational force here, m2g, is at 98 newtons. The gravitational force times sine theta, sine of 30 degrees, 30 degrees, 30 degrees? Was it 30 degrees before? It was 37. Okay, I think. Is that what, yeah, that does. Oh, no, it's at 37. I think I've changed the number. I changed the numbers. I thought they had changed them, but I think it was me. So I got to go back and recheck this one. All right. In any case, what we've got here, yeah, I got to go back and check this. I'm picking up the 30 degrees from an earlier example. So this is at 37, and I need to go back and recalculate. Both of these, actually, will change. So let me go ahead and work from the 30 degree angle, which now I've got to go back and check and see if, I'm pretty sure this, I calculated it for 30. So at 30 degrees, this is 49 newtons. And at 30 degrees, this works out to be 25.5 newtons. And dividing through by the 20 kilograms, I ended up with an acceleration of 1.18 meters per second squared. Okay, so again, I need to go back and double check that one. All right, we have, I think we're coming up on time here. Let me see. So we've spent a good amount of time looking at friction, And we've looked at a lot of good examples, so these are all really good examples to be taking a look at. Now we want to move on into another major topic of the course, not the course, sorry, it's a major topic of the course, and that is circular motion. So chapter 5, we start out by looking at friction. Now we're going to start looking at circular motion. If I have something going around in a circle, and at least for now, let's imagine that the velocity is a constant. So if I've got a velocity here and then a velocity here, well, there's an acceleration taking place. So, you know, this object is accelerating. Let's take a little bit of a more detailed look at this. So let's say that we have something going around in a circle. Circular motion is really common, so we're going to be using circular motion a lot. So let's take a look at point A. I've got a velocity here, and then by the time I've traveled to point B, that velocity direction has changed. Now, what we could do is we could look at one of those, you know, limits from calculus, saying by how much has the velocity changed, and what was the time interval? So is this happening really fast, or is it happening more slowly? Now, the way that we look at these vector diagrams, here is V1, here is V2, what we can do is we can pick up those two vectors and move them over to a separate, what we consider to be a vector diagram. And from there, we can analyze what's happening in terms of delta V. So it used to be that the velocity was here, but now it's shifted. So my delta V is actually in a perpendicular direction. Now, I think we've seen this before, but in any case, I've got velocities that are traveling, the delta V's are perpendicular to the V1 and the V2 in the limit as we look at smaller and smaller time intervals. Now, from this, what we're going to be able to go in and show is that for circular motion, A is to V as V is to R. We can show that ratio. Now, the way that typically gets written is this. This becomes one of our kinematic equations for circular motion. Let's see how that gets derived. So again, if we go back to the previous diagram, what I want to do first of all is start out with R vectors, displacement vectors. So for circular motion, it's very handy. See how we have the R here and the R here? Well, I want to write those in terms of vectors also. So here's the way it works. R1 is here, and then at a later time R2 is here. We're using the center of the circle, center of the circular motion, as an origin to our coordinate system, and then that turns out to work really well. So these magnitudes are the same, but dr is in a perpendicular direction, and so the magnitude of dr is given by dr. So if I take a d theta here, d theta will be equal to the arc length divided by the radius. Now you guys don't have to know the details of this derivation, so this is one of those, we'll have these examples from time to time where I'm going to go into a little bit more detail to see how some of the formulas are derived, but for this one, this is not required, it's just kind of interest. So I can write this as d theta is dr over r. Now dr is in the direction of v. V is always going to be in the direction of dr. So this is the direction we're traveling, is the direction of dr. So I can write that as v dt over r. Now there's also the velocity diagram that we saw on the previous page. Well, this triangle, the velocity vector triangle, is similar to the displacement triangle. So we can say the very same things. V1 magnitude equals V magnitude. We're just going to call that V. The magnitude of the dv vector is dv. And so we can write down the same equation, or a similar equation, and when we cancel, since these are equal to each other, we can set this equal to this, cancel out the dt's, and that gives us this nice ratio of, well, this is really dv to v is equal to dr by r, and the dRs and the dVs can be changed into accelerations and velocities. So that's the ratio, and then the formula that comes from that is this. And so here is the formula. Again, I always like writing it as A divided by V equals V divided by R, but that's, the A is equal to V squared over R is the way it typically gets written. So this is what the accelerations look like, and we'll stop here. If I'm in circular motion, the dVs are back towards the center, and that says that's where the acceleration is. So if I'm traveling along in a direction and I start moving to the right, I'm actually accelerating in that direction, in the right direction. If I begin to veer to the left, that's the direction of my acceleration. So again, I think we want to stop and take a break here, and then we'll come back and look at this in a bit more detail. Any questions at all, just stop by and let me know what questions you've got.